This is an AS Decision 1 question on Dijkstra's algorithm. The network in Figure 2 shows the direct roads linking 5 villages A, B, C, D and E. The number on each arc represents the length in miles of the corresponding road. The roads from A to E and from C to B are one way as indicated by the arrows. Part A. Complete the initial distance and route tables for the network provided. Okay, we'll start with the easier part, which is filling in the initial route table, and that's just going to be copying the column headings into each column. So we'll have A's in the first column, B's in the second column, and so on. Now we'll move on to the initial distance table. Now remember that a town or a node or vertex going to itself, we just put a dash in. So we'll start from A to B. So if we go from A to B, that's 15, and it's two-way, so B to A will also be 15. A to C is 7, and because it's two-way, again, C to A will also be 7. A to D is 18, it's two-way, so I'll have 18, A to D and D to A, and A to E is 3. Now this is only one way, so I'll have a 3 from A to E, but when I go from E to A, I'll put an infinity symbol to show that this is only one way, so we can't go along that route, so we'll have an infinity symbol there. Now moving on to town B, we can go from B to C. Well, we can't go from B to C. You can see it's one way. We can go from C to B, so we'll have an infinity symbol from B to C, but from C to B we'll have 5. Then B to D, there's no direct route there, so we'll have an infinity symbol there, and then B to E, again no direct route, so infinity symbol, and that's going to be the same from D to B and from E to B, where there is no direct route. Moving on to town C, we're looking at how we get from C to D. That's going to be 4. That's two-way, so we can have 4 in these two boxes here and here. And then C to E, that's also two-way, so we've got 9 and 9. Then move on to town or vertex D. So D is here. Can we go from D to E? Yes, we can, in both directions, and that's a distance of 3. So that completes the initial distance table. Part B. Perform the first 3 iterations of Floyd's algorithm. You should show the distance table and the route table after each of the 3 iterations. So the first thing I need to do is to copy down the first row and column and the diagonal from both the initial distance table and the initial route table into these empty tables ready for the first iteration. Next, I'm going to highlight the first row and column, or the row and column that I've just copied down. I'm going to highlight those. Next, I'm going to add together the numbers in the row and column that I've just copied, compare those to the values in the original distance table, and if the value that I get by adding the two numbers together is lower in this first iteration of the distance table, I change its value to the lower value, and I change the letter in the route table to A, because that's the row and column I've got highlighted. So we'll start here. 15 plus 7 is 22. 22 is less than infinity, so we change, and I'll put all the changes in green. So change the value, change the letter in the route table to A. So this now gets changed to A because it's the A row and column. Next value, 15 plus 18 is 33. 33 is less than infinity, so change the value, change the letter. Last one, 15 plus 3 is 18. 18 is less than infinity, so change the value, change the letter. Moving on to the C row, 15 plus 7, or 7 plus 15 is 22. 22 is greater than 5, so no change to the value, no change to the letter. Next one, 7 plus 18 is 25. 25 is greater than 4, so no change to the value and no change to the letter. This cell here, 7 plus 3 is 10. 10 is greater than 9, so no change to the value and no change to the letter. Next row, 18 plus 15 is 33. 33 is less than infinity, so change the value, change the letter to A. Next one, 18 plus 7 is 25. 25 is greater, so there's going to be no change to the value and no change to the letter. And then the last one here, 18 plus 3 is 21. 21 is greater than 3, so no change to the value and no change to the letter. Last row, here we're going to have infinity plus 15. That's greater than infinity, so no change to the value, no change to the letter. Infinity plus 7 is greater than 9, so no change to the value, no change to the letter. And the last value here that we need to work out, infinity plus 18 is greater than 3, so no change to the value and no change to the letter. So we're going to start by copying the values in the second row and column and diagonal from both the distance table and a root table into our new distance and root tables ready for the second iteration. Now I'm going to highlight this second row and column. I'm going to add together the numbers in the rows and columns and compare them with the previous iteration and make changes if those values are lower. So we'll start with here. So 15 plus 22, that's going to give us 37. 37 is greater than 7, so no change to the value and no change to the letter. Then we have 15 plus 33, that's going to give us 48, greater than 18, so no change to the letter, no change to the value, 18, and no change to the letter, so that remains as D. And this one here, 15 plus 18, that's going to give us 33. 33 is greater than 3, so no change to the value and no change to the letter. Next row, which is going to be the C row, 15 plus 5 is 20. That is greater than 7, so no change here, no change to our letter. That had an A there before, so that change stays as an A. This cell here is going to be 5 plus 33, which is 38. Now 38 is greater than 4, so again no change here, no change, and that is the letter D. So no changes so far. And here we're going to have 5 plus 18, that's 23. 23 is greater than 9, so no change to the value, no change to the letter, and that letter that was there in the previous iteration is E. Moving to the next row, here we got 15 plus 33, which is 48, greater than 18. Again, no change here, and no change here. Moving on to this one here, we've got 33 plus 22, which is 55. 55 is greater than 4, so no change to the value, no change to the letter. Let's have a look to see what letter was there. It was a C, so that remains as a C. And the last one on this row, we're going to have 33 plus 18. That will be 51. 51 is greater than 3, so no change here. And no change here. That remains as an E. Bottom row, Here we're going to have infinity plus 15, which is greater than infinity, so no change, and no change. Here, infinity plus 22, again it's greater than 9, so no change to the value of 9, no change to the letter. Now that would have been a C, so C is there. And then the very last value, we have infinity plus 33, that's greater than 3. So the 3 remains, and the letter that was there before, the D, remains as a D. Now let's copy down the third row and column and the diagonals from the previous tables ready for the third iteration. We'll highlight that third row and column, and then here we'll do 7 plus 5, which is 12, which is less than 15, so we have a change, first one for a while, to 12 for that value, which means we're going to change this letter here to C because that's the row and column that we are now using. We'll move on to here, 7 plus 4 is 11, that's less than 18, so we've got a change here for this value and a change to this letter. And then we're going to have 7 plus 9, which is 16, that's greater than 3, so no change here to this value and no change to the letter, so that's going to remain as an E. Moving on to here, 7 plus 22 is 29, greater than 15, so no change to the value, no change to the letter, that stays as an A. And when we get to here, this will be 22 plus 4, that's 26, that's less than 33, so there's going to be a change to that value to 26 and a change to this letter to the letter C. And the last one on this row, we have 22 plus 9, which is 31, greater than 18. Okay, so no change here and no change to the letter that was here, and that was an A. Then we move down here, 7 plus 4 is 11, less than 18, so we have a change to the value and a change to the letter to a C. 5 plus 4 is 9, less than 33, so we've got a change to the value and a change to the letter. This one here is going to be 4 plus 9, 13, greater than 3, so no change to the 3 and no change to the letter. There was an E there before, it stays as an E. Bottom row, 7 plus 9 is 16, that's less than infinity, so a change to the value and a change to the letter. Here, 5 plus 9, 14, less than infinity, so a change to the value, a change to the letter. Let's be consistent, that letter there, first C, should be in green as well. And then we're on to the last one. This will be 4 plus 9, which is 13. It's greater than 3, so no change to the value and no change to the letter. That was a D, so that's going to remain as a D. After 5 iterations of Floyd's algorithm, the final distance table and partially completed final root table are shown below. First part of part C, what we need to do is to explain how the partially completed final root table can be used to find the shortest route from E to A. So what we need to do is to explain in words how we would do that. So the first thing that we would do is we would start in the E row in the 5th row of the table. Then we look to see if there's a letter in that row and the column of A. Yes, there is, and so that tells us that there's a route from E to A via D. We then look to see if there's a route from E to D, which there is, so that's just going directly to D. That's going to be the minimum shortest route. Now we've got from E to D, we still need to get to A, so we go to D and see which route is the minimum route, if any, to get to A, and that's going to be via C. And we can confirm that that is going to be the shortest route, because if we go to C, that will take us to A. Okay, so that completes the explanation of how we can use this root table. And the second part of part C is asking us to state what this root is. So we know we're starting at E and we're getting to A. So from the root table, we saw that if we want to get to A, we need to go to D first, or via D. Then from E, then we're going to D, and again from the table, from D we're going to C, and then C to A. So E, D, C and A. Mubin 2 decides to use the distance table to try and find the shortest cycle that passes through each vertex. Starting at D, she applies the nearest neighbour algorithm to find the distance table. First part of part D, we need to state the cycle obtained using the nearest neighbour algorithm. Part D and the first part of part D, what we need to do is to state the cycle obtained using the nearest neighbour algorithm. Okay, so we will start from vertex D. Its nearest neighbour is a weight of 3, and that's E. From E, the nearest neighbour, well, it can't be A. Well, A is its closest neighbour, but we can't go back along this route. So the next nearest neighbour is C, where we will go to here. The next nearest neighbour is B, on this route here. And then the nearest neighbour from there is A. And then from A, we need to return back to D. So using the nearest neighbour algorithm, we have a route of D, E, C, B, A, D. Now, second part of part D, what it's asking us to do is to state the length of this cycle. So what we want to do is to find the shortest way to get between these vertices. So D to E, well, that shortest route is just going to be 3. Then going from E to C, that's got a weight of 9, but I can get to E to C quicker by going from E to D and then from D to C. So that's going to be 3 plus 4. So that's actually 7 to get from E to C, which is shorter than 9, so plus 7. Now from C to get to B, well, I can see by inspection that that shortest route is going to be along this directed arc here. That's going to be 5. Then from B, I want to get to A. Well, its shortest route is going to be 15. That's really the only route because I can't go back along to C and then back to A. If I could, then this would be slightly shorter. So that's going to add a weight of 15. And then from A, I want to get back to D, and my shortest route is going to be to E and then to D. So that has a weight of 3 plus 3, which is 6, which is less than 18. So I want to add another 6. And if I add all of those together, I've got 10 plus 5, 15, plus another 15, 30, and 6. And that's going to be 36. And the units for this is going to be in miles. Now we're on to the third part of part D. And this is saying that we need to interpret the cycle in terms of the actual villages that have been visited. So we had to go sort of backwards and forwards to get those shortest distances. So let's just rub this out and let's actually look at the route that we took. So we started at D. Let's write that down. And then we did go directly to E. So we went along here like this. So we went to E next. And then to get to C, we actually went back to D. And then from D, we went to C to take a shortcut to save some mileage. So from E we went back to D, and from D we went to C. Now C we went directly to B, and then B we went directly to A, and from A we wanted to get the shortest route back to D again. That we took the route that took us to E and then to D, so E and then D. And finally, the last part of part D, and it says prove that Menintu cycle is not optimal. Now, there are different ways that I can show that her cycle is not optimal. One way is basically to find a route that is less than 36 miles. Now, we don't necessarily need to start at vertex D, but I'm going to see if I can find a better, shorter route starting from vertex D. So I could start at D, and then from D I could go to C, so that gives me 4, and then from C to B, so I've now got a weight of 9, and then to A, so 9 plus 15 gives me 24, and then 24 plus 3 to get to E, 27, and then plus another 3 to get back to D again. So I can simply write down that route that I've found, D, C, B, A, E, D, is equal to 30 miles, which is less than the 36 miles that Mabintu found previously using this nearest neighbor algorithm.